Welcome back, and in this series of videos we're going to be looking at the industrial applications of inorganic chemicals. We're going to primarily focus on catalysts and a particular cancer drug called cisplatin. So you're going to need your notes, and we're starting on page 2. So if you remember back to our work from lower 6th, a homogeneous catalyst is one where everything is in the same phase. And a heterogeneous catalyst is different phase, or different phases. So that's the simple definition between the two of them. Try to use phase rather than state here. It's a good way of separating them. Industrially, we always want to use a heterogeneous catalyst because it's much easier to separate it from the reaction mixture if it's in a different phase. So these heterogeneous catalysts are ones which are used most predominantly in industry. Homogeneous catalysts can be things like enzymes, and they tend to be in the same phase as the reactants. So heterogeneous catalysts always proceed in the same 3 steps. Adsorption, and be very careful of that D. This is a surface reaction. So the reactants are adsorbed onto the surface. There is some sort of reaction, and then the products are desorbed from the surface. So the strength of the adsorption onto the catalyst is very important. If it's too strong, then the products will never be able to desorb. If it's not strong enough, they won't be able to adsorb onto the surface long enough for the reaction to take place. So there's a kind of a sweet spot here in the middle. You don't want too low activity where the adsorption is too weak. You also don't want it where the absorption is too strong. And that's why most of the good catalysts live in this sweet spot here. A classic example of this is on page 3, and it's the catalytic converter in a car, which turns carbon monoxide and nitrogen monoxide into slightly less harmful carbon dioxide and nitrogen gas. So, first point, the CO and NO are adsorbed onto the surface. That's the first bit. They have to stick onto the surface. This binding weakens the bonds, and allows a reaction to occur. And lastly, the carbon dioxide and nitrogen desorb from the surface. So you've got those 3 steps. They're adsorbed onto the surface. By adsorbing onto the surface, they're forming a bond with the surface. This weakens the bonds within the carbon monoxide and within the nitrogen monoxide. That allows the reaction to take place, and the carbon gains the oxygen and the nitrogen loses an oxygen to become carbon dioxide and nitrogen. The one pollutant which is not removed via the catalytic converter will be sulfur. And in fact, you want to do that quite early on before the fuel gets anywhere near your engine, because sulfur can actually poison the catalyst. So remember, poisoning is where something binds irreversibly to the surface, to the active site, and therefore blocks that active site. Another good example is the contact process making sulfuric acid. So sulfur is burnt in oxygen to produce sulfur dioxide. It's then reacted in a catalytic bed reaction to convert the sulfur dioxide into sulfur trioxide, and then you're adding water to that to make sulfuric acid. We're interested in this step 2, how the sulfur dioxide is converted into sulfur trioxide using vanadium pentoxide as a catalyst. So the vanadium starts its life as this V2O5 vanadium pentoxide. So here the vanadium has a plus +5 oxidation state. In the first step, it's going to be reduced to the V2O4, which is the +4 oxidation state. So it's reduced in the first step. Sometimes you will also see this written as VO2, where the vanadium is still, though, notice, in the +4 oxidation state. So V2O4 or VO2, both vanadiums are in the +4 oxidation state. So the SO2 coming in binds to the surface of the V2O5 reaction, and we get our V2O4 and we get our SO3. So that's the first step. But then we need to regenerate this catalyst, so the V2O4 then has a chance to react with the oxygen, the O2, and half of that, to make V2O5 again. Now, if you add these two reactions back together again, you basically just get the reaction we started with, because the vanadium species will all cancel, and we will get SO3. We add those two reactions together. So the SO2 is adsorbed onto the surface of the vanadium species to make the sulfur trioxide. The vanadium V2O4 then can react with the excess oxygen to remake V2O5. So this was an exam question from a couple of years ago where it asks you to write the overall equation and, for 6 marks, explain the catalytic behaviour of the V2O5 in the reaction. So what I'd like you to do now is to pause the video and have a go at explaining that catalytic behaviour. So, as we said before, it's really important that you state the blindingly obvious. So the first mark is for actually just saying that the vanadium is acting as a heterogeneous catalyst. Then we go through the similar steps as to before. So the SO2 is adsorbed onto the surface where it can react with the V2O5. The SO3 that's formed is only weakly bonded from the surface, so it desorbs from the surface. So the oxygen can react, regenerating the V2O5 catalyst. So this reaction is following a different mechanism with a lower activation energy. Notice that the SO2 and the oxygen never react directly together.